Today I am going to talk about testing. I will discuss the problems with the traditional approaches to testing and propose our solution to these problems, the Snabbkaffe test framework. But first of all, I'm going to briefly give you a little background to explain why our team chose to invest in the advanced test tooling. Okay. Sorry about this. PDF is not very good for presentation, apparently. So our team works on EMQX, the world's most scalable MQTT message broker. It's used in Internet of Things, industry, connected vehicles, gaming, and many other applications. It's written in Erlang, and it is fully open source. So what is MQTT? It's a lightweight pops-up messaging protocol, which is an OASIS standard, which features minimal resource footprint and network bandwidth utilization. Also, it supports bidirectional communication. So, for example, your IoT device can send sensor data to the cloud and receive the commands back. And also it supports reliable message delivery. So what technical challenges do we face when we develop this system? EMQX broker is a very complicated system which supports multicasts, asynchronous and delayed message delivery scenarios. It has gateways for protocols other than MQTT. Of course, it supports clustering. It is fault-tolerant. And last but not least, we use Mnesia. Recently, we've unlocked an achievement of serving 100 million simultaneous clients in a single EMQX cluster. This was done by improving horizontal scalability of Mnesia database, which is used to store routing table and session information. In no small part, it was done thanks to Snabbkaffe testing. So it's not just some sort of theoretical concept, it's a production-grade library. Before introducing Snabbkaffe test framework, we'll revisit the thought process that led to its inception. We will use some math to find the answer as to why the test cases are flaky. Then, using this knowledge, we will try to assign difficulty level of testing to different classes of programs and try to find the optimal test framework for each of the classes. Before going any further, let's briefly discuss the standard approach to testing used by the majority of programmers. You will recognize it immediately as I speak. Let's imagine that we have some reasonably complex system, say an OTP application. So what does a typical test case look like? First of all, we prepare the system in a known state. We need to configure our application, possibly set up the mocks, and start it. If the system interacts with a third-party service, say Kafka, we need to prepare it as well. In the end, this gives us a system in a known state. When we interact with the system in a controlled way, call some APIs, send some messages, or interact with REST endpoint. Then we inspect the state of the system and assert correctness. This is where the actual testing takes place. For this reason, I call this approach state-based. Then steps 2 and 3 can be repeated, or you can just stop the test case and do a cleanup. It's important that the person writing the test understands how the state of the system changes after each interaction. So we must maintain some sort of model of a state. This model can be implicit or explicit when stateful property-based testing is used. I want to emphasize the statement since it's crucial for understanding the philosophy of Snabbkaffe test framework. Let's go through the different classes of programs and see what does it take to model their state. The first class of programs what we're going to discuss is pure functions. Since we are using a functional language, these functions have a nice property. For the same input, they always return the same output. Like it is shown on this picture, our program takes a value and maps it to another value. Programs like this are called deterministic. And if we want to build their mathematical model, we just borrow the definition of function and use it more or less as is. It should not be a surprise to anyone familiar with a functional paradigm because it's one of its main selling points. So what about testing pure functions? It's not hard at all. So we assign casual difficulty level because proper library and other property-based testing libraries work like magic for this type of programs. Next, let's step it up a little and talk about the stateful system. Mathematically, they're similar to pure functions. We can also translate them to the mathematical definition of function directly with an added state argument, which is passed through the chain of pure function calls. Overall, the stateful system is also deterministic, because repeated application of a deterministic function always produces the same result for the same input. So from testing perspective, the difficulty level is easy, and we can use stateful property-based testing here. But this is also the difficulty level where we encounter a model of a state space for the first time. But for now, it is very tame, and stateful proper does a great job maintaining it for us. The problems begin when your program starts to interact with the real world. The real world is unpredictable, so we can no longer model it using deterministic functions. Input-output is not deterministic. So, as is shown on this picture, now our function f can return multiple values for the same input. So what are the sources of random behavior? Network, where packets can be lost, reordered, or even mutated. Hardware failures. And also we have humans who interact with our system, and we can never be sure what we're up to. So non-determinism is an inherent property of real-life systems, and we have not even touched concurrency yet. If we talk about repeated application of non-deterministic functions, we get the following picture. Calling a non-deterministic function f with m outcomes n times produces m in power of n results. Every circle on this picture represents one of the possible states of a program, and arrows represent state transitions. So as you can see, the state space grows exponentially with each call. How do we classify non-deterministic algorithms in general? The difficulty level is normal because it's a typical real-life system. But when we talk about testing, things aren't that rosy. In practice, I have not seen many attempts to deal with a state space explosion. Usually, test cases are written to interact with the system very carefully to avoid dealing with non-determinism. So in practice, the test cases ignore this problem. But as we just discussed, randomness is an inherent property of real-life systems. So it creeps into our test cases and it makes them flaky. If you want to be serious about this problem, the tools are out there. You can either use case engineering or go with specialized model checkers, such as TMA+. Next up, there's concurrency, and it makes things much, much worse. Suppose we have two processes, A and B, that perform an A and an B operations correspondingly. The process scheduler is a black box, so we consider its behavior random. What is the number of possible ways to schedule these two processes? To answer this question, we first notice that the length of the resultant trace is equal to an A plus an B. For a while, we forget about the process B and focus on A. We need to find all possible positions for A's operations. When we have just one way to fill the rest of the positions with B operations. If we apply some simple combinatorics, we will arrive to this nice formula. It denotes the number of possible ways to schedule two processes. If you consider that each unique scheduling may lead to a different state of the system, the size of the state space of a concurrent program grows super exponentially with the total number of operations. And this is really bad news. So the difficulty level is hard, but thankfully there are advanced tools to help us with testing concurrent systems, namely model checkers, such as Concurrency. Now let's take a look about a typical Erlang application assembled together. It is concurrent, it is fault-tolerant, it interacts with the real world, it is distributed, so it interacts with the network. So the difficulty level is nightmare. But not everything is so grim. If you listen to Joe Armstrong's lectures, it is clear that he and the OTP team were very well aware of these problems from the very beginning. So the mitigations for the state space explosion were built into Erlang's design. The first mitigation is let it crash paradigm. When the system detects that it has entered an unexpected state, shown in red on this graph, it crashes and it gets restarted, returning to the known state, shown as solid green on the graph. This can be modeled as culling of the state space using restarts. While it makes our lives as programmers much easier, it presents a challenge for the state-based testing, since the supervisor is a black box which has its own state, which we cannot model. Another mitigation is process isolation. Each process has its own heap, so the overall state of the system is partitioned. Therefore, most operations commute, and only schedulings of non-commuting operations increase the state space. This is why tools like Concurrency can be relatively fast. But from the perspective of state-based testing, it presents another challenge. The partitioned state is harder to inspect. Let's summarize the problems with a traditional state-based approach to testing. State space of a concurrent system that does input-output grows super exponentially with the number of operations in the worst case. So any state-based test case has to implicitly model this state space. And it's practically an impossible task. So the test cases tend to be flaky. In Erlang, we also face the additional challenges. Supervision trees are often untested. and state of processes can be hard to inspect. So what is our solution? Just ignore the state. If I need to describe the core idea behind Snabbkaffe test framework in just one sentence, it would be this. If humans can find bugs by looking at the logs, so can computers. Let's unpack it. Any programmer worth a salt can investigate a problem that happened in the past on a remote system without direct access to the system. We do so by looking at the logs and building up the mental model of what went wrong. We can even derive a subset of a faulty state space just by reading the log messages. So why don't we teach computers to do the same? And why don't we do this in CI before the bugs happen in production? This is the idea behind Snabbkaffe. So what is Snabbkaffe test framework? It was designed primarily with concurrent, distributed, fault-tolerant, and asynchronous systems in mind. It does the trick by moving the focus from states to the traces. It supports advanced modes of testing, such as chaos engineering and scheduling injection. It's built for efficiency. It allows you to run your system once and verify multiple properties. It brings speed and stability because it totally eliminates sleeps from your test cases. If you compare it with a state-based approach, we notice that the number of trace events scales linearly with complexity of the test scenario, as opposed to the super-exponential growth of the state space. State-based tests inspect series of snapshots of the system, while trace-based tests inspect the whole execution history of the system, so there's no need to wait until the system stabilizes to take a snapshot. Now we can test the system in motion. And most importantly, some of the properties of asynchronous and eventually consistent systems can be more easily described in terms of trace specifications. But enough about philosophy, let's talk about practice. Every Snabbkaffe test case is split into two stages. Run stage, where the program runs and emits the event trace, and check stage, where the trace is collected as a list of errant terms and it's validated against the specs. In order to start using Snabbkaffe, the system must be manually instrumented with trace points. It's done by replacing your regular logs with structured trace points using macros from Snabbkaffe library. Our industry is already moving towards structured logs and logging with JSON, so it's a good idea anyway. Let's take a look at some of the examples. There are two types of trace points. Ones that disappear from the release build, so they don't hurt the performance, and ones that become regular logger messages in the release build. Such trace points have severity as an argument. Each event has a kind identifying it and additional data expressed as a map. And this is what the collected trace looks like. It is simply a list of events where each event is represented as a map. The kind, the additional data, and the logger metadata are all present there. Erlang supports distributed computing out of the box, and so does Snabbkaffe. It is possible to forward trace events from the remote nodes using this function. All features, including fault and scheduling injections, will work in the distributed environment. An often asked question, why don't we just intercept logger messages? The answer is that using a different trace API helps indicating what a lock message is used by the tests, because usually programmers don't expect that changing a lock message can break the tests. Also, trace point macro does much more than just logging, and this is something we will discuss later. Another question is, why don't we use debug traces? It was also a conscious decision. Debug traces are tightly bound to the structure of the code. So refactoring the code or adding an argument to a function would break the tests for no good reason, and we don't want this. Also, log messages are typically placed in interesting places. So if some event is interesting for humans, it is likely to be interesting for the tests. Let's take a look at the check trace macro, which is used to build Snabbkaffe test cases. It has two arguments, run stage and the check stage. Once the run stage completes, the trace is collected and passed to the check stage callback, where it can be inspected. As I mentioned earlier, one of the benefits of trace-based testing is that checks are separate from the program execution and from one another. Because of this, it's possible to check multiple properties at once, as shown in this code example, where the check stage consists of a list of callback. Each callback has to succeed, so we can consider the test successful. Check trace macro supports some additional arguments, for example, time trap. It is helpful since if the run stage times out, Snabbkaffe will dump the trace collected so far and other debug information to help with investigation. I'll briefly mention that it's possible to combine property-based and trace-based testing to some extent. And Snabbkaffe has a helper macro that helps to integrate with proper. One of the goals of Snabbkaffe is total elimination of sleeps from the tests. Now let's see how it's done. Snabbkaffe allows to inspect the trace of the system while it's running. For example, there's blocked until macro, which blocks the execution of a process until an event conforming to a match pattern is emitted. Once such event is produced, the execution of the blocked process proceeds immediately. So you don't need to add any sleeps or poll any state. It's much faster and less prone to flakiness. Speaking of the check stage, implementing it is very easy since the trace is just regular Erlang list with regular Erlang terms. So it can be processed using any pure function. There is a number of helper macros that help filtering and transforming trace events, which can be found in our documentation. But of course, you are free to use list filter and list comprehension and whatnot. My favorite kind of helper macro for the check stage is strict causality. It helps finding pairs of complementary trace events representing the cause and the effect of some action. It takes three arguments: a match pattern that searches for the cause, a match pattern that searches for the effects, and the trace. For example, it can verify that for each request there is a response from the system, so every request is fulfilled. Variable bindings from the cause match pattern are propagated to the effect match pattern, and to the additional guard expression as well. For example, if we want to test a base64 server, we can just start it, bombard it with requests from thousands of parallel processes, and all we need to test the correctness of the server's implementation is this little trace specification. If you want to inspect the pairs of events explicitly instead of just verifying the absence of causality violation, it can be done using find pairs macros. Now let's talk how Snabbkaffe helps to test fault tolerance of Erlang applications. Taking fault tolerance seriously is one of the selling points of Erlang, and we do so by organizing our applications into supervision trees. Designing and tuning supervision trees is sort of an art, and Snabbkaffe allows to test them by deliberately injecting faults into the system. Any trace point can be also used to inject errors into the system. It's done using inject crash macro in the run stage. Its first argument is a match pattern for the trace event that must result in error. And the second argument is fault scenario. Snabbkaffe can simulate random, recoverable, and unrecoverable faults using different fault scenarios. Also, different fault scenarios can be combined in the same test. The final feature what I want to mention is manipulation of a process schedulings. Sometimes it is necessary to test a certain process scheduling. For example, suppose normally an event foo occurs after event bar, and everything works just fine. But in rare case, the opposite happens and the bug occurs. Imagine working on a bug fix for this problem using test-driven development style. Snabbkaffe can manipulate scheduling of the system. It's done by invoking force ordering macro in the run stage. This macro takes two arguments, two match expressions, one for the event that must happen first, and another for the event that must be delayed until the first event is emitted. Please keep in mind that, of course, this macro can introduce the deadlocks if the injected scheduling reverses the natural causality of the events. In the future, we will try to detect this situation in some cases. So to illustrate all the concepts that I described previously, let's talk about one of our projects that uses trace-based testing extensively. It's related to improving horizontal scalability of Mnesia database. EMQX uses Mnesia to store the following data: the routing table, topic metadata, configuration, and some more. We use Mnesia because it gives us very fast read access, so it's possible to read from the tables in rather hot loops. But its problems are also very well known. In particular, it's hard to recover the cluster when it fails, and Mnesia has some problems with horizontal scalability. Let's briefly go through Mnesia commit protocol. In the simplest case, it uses mesh topology, where all the nodes are equal. There are different commit protocols in Mnesia, but we are talking about the simplest case. Every node holds the locks. All the nodes participate in the two-phase commit protocol, so the more nodes you add to the cluster, the more negotiation is needed to commit the transaction. So our approach is to go away from full mesh topology by extending the replication protocol and making it eventually consistent. The heart of our solution is replica state machine, which has two main states. Disconnected, where the node tries to discover the other nodes that have a source of truth. Bootstrap, where the node copies the data from the upstream node using dirty operations. Local replay, where the node applies the upstream transactions buffered during bootstrap stage. And normal state, where the transactions are applied in real time. This state machine is very complicated because it must ensure that the data is consistent. We don't want any bugs. It must recover from failures, and it should never block the other nodes. And it must be fast, since sometimes we deal with large bursts of write operations and transactions. Every time the state machine enters a new state, it emits a trace event. This snippet of code was taken from the actual code base. For the data consistency, it is crucial that the state machine goes through the states in the order I mentioned previously. So how can we verify it using trace-based approach? Trace specification that verifies the correctness of the state transitions looks like series of invocations of causality macro, similar to this code snippet. This looks very unusual from how you test state machines using proper, for example. So what are the benefits of this approach? First of all, the trace-based model is much simpler. We don't need to implement tons of callbacks. We just write a couple of macros. So we only specify the expected causal relationship between the state transitions as pure function operating on a list of historical events. Execution of a test case and verifying the properties are completely untangled. With this approach, we can test a fully assembled application together with the supervision trees. We can test a distributed system running on multiple nodes. And this specification does not care about the exact times of the events, so it can verify properties even if the state machine process crashes and restarts. And this is what we do in one of our test suites. The following snippet injects random crashes into the database engine. Then we throw thousands of random transactions into the system and verify that the transaction importing operations do the right thing by inspecting the trace. And all of this is done in less than 200 lines of code. I've finalized this presentation by giving an example of scheduling injection. We want to make sure that the replica state machine handles transactions correctly when it's in all of these possible states. We generate transactions using a process that increments a counter in the database. When we synchronize the transaction generator process with a replica state machine, finally we verify that the observed state of a counter in the table replica by inspecting the trace. So this is the code that does the scheduling injection that I described previously. Conclusion. Recently, we've released version 1.0 where the API has been frozen. I skipped over tons of functions, but you can read about them in our documentation. Our website contains examples that explain how the APIs work, so I hope it will be useful. Snabbkaffe library is being actively developed, and we have some big plans, for example, supporting trace point in NIFs. And of course, your suggestions, bug reports, and patches are welcome. You can find examples of large Snabbkaffe test suites in action in the following project: EMQX, Quicker, MRI database, Broad, and Kflow. And this is it. Thank you.
Thank you very, very, very much. Are there any questions? I didn't see anything in Hoover yet, so please raise your hand if you have anything. I'll ask one in the meantime. So this looks amazing, and I cannot help but think how all this implemented and be really, really excited. I'm wondering how much, what's the attitude into injecting all these events into the application code rather than into the a separate part of the test code? Is this something that is that you get attitude about? People are sometimes reluctant to add this kind of things in the production code, let's say.
Yes, this is one of the limitations of this library because you need to invest in it. But as I mentioned, in all the modern applications, you kind of need to use structured mock messages. So you can use mock indexing. So for example, if you use Google Cloud, the mock processing is expected to use JSON. So if you move in towards this direction, you can as well use Snabbkaffe trace points.
Mm-hmm. Any questions? Yes. I can bring the mic.
Thank you. I've already posted it in Hoover. So I was wondering if there is a tool for gathering some Snabbkaffe events from currently running application in prod, so we can reply them, and use that to create some sort of golden master test to start with. That would be interesting, I would say.
Yeah, this was not a use case that we thought about during implementation. So currently, the traces are emitted only when you build your code in test mode. So most of trace points they simply disappear from your prod build, so they don't affect performance. And the rest of traces they simply become logger mocks. So you cannot really collect Snabbkaffe traces from the prod application, and I guess it will be quite expensive as well, because these injections that I described, they're pretty optimized, but they're still consuming some resources. So yeah, it's really something that you only want to use in your test suite.
Yeah, that's totally logical. What I'm saying is I'm starting with an already existing system. It's not well tested stuff, blah, blah. So I could deploy it once with that tool and somehow capture the current behavior just once. And then, yeah, after that I remove it and I continue with the normal workflow of Snabbkaffe.
Essentially convert this into a scheduling constraint on the system in some way,
yes,
right?
Something.
Okay. As I mentioned, we have not thought about such use case, but if you raise an issue on GitHub, we'll try to think about it.
Sounds like you have things to talk about. More questions? And I think there is nothing on the Hoover app. Let me quickly check once more. Otherwise, thank you very much, Dmitrii, for your talk.
Thank you.